職業，定係你睇埋天文啊？定係睇埋星星啊？
我冇嘅。
係嘛？
你知天文數啦，跟住有啲真係睇天文嘅人嘅。
啊真係，
之後我跟住係咩嚟㗎？
天文所係嗰啲四大人。哦。
跟住佢哋有啲人 send 啲天文嗰啲相，我覺得㗎嘛。跟住啲總華 send 咗M78星雲，你知咩？鹹蛋超人。
哦。
我想知你有幾多時間練波啊？你一個禮拜？
幫手執完出面啲嘢，執幾多嘢啊？
咩啊？你有幾多時間練波
6至10個千
一個禮拜四個鐘。
2節啊，1、3。
哇！咁咪正咯！屌，我哋得4個鐘練嘅男嘅一齊練。
就係死喎！
仲要咧，星期二嗰節咧得半個場咯。
佢話其實我唔係想打波先入嗰啲咩，我係想入大學咋。
咁點解你會入咗手球咧？
不過我想入大學咯。
你一定要你揀過咩？
係啊。
哦。咁你梗係揀啲冇人識嗰啲啊咩？
又蛙艇咯。
球啊
！6點鐘起身入到去，一定入到，包你入到。
蛙艇雞婆
又辛苦。
蛙艇你不如做 gym。
有隻狗咁。
你去蛙艇不如做 gym，啲龍舟嗰啲係黐線。
啲男仔。
How about now?
有冇嚟到？
Yes, I think.
有。
Yes. Okay. Okay. So I say again. So I asked you to come today. It is because I try to persuade you to leave this team. Rather than ask you to join the team, rather than ask you to learn something from me, I ask you to leave the team. And why? Because I say, based on my experience, this team, it is not suitable for some of the students. Okay, so do you know why? I think some of you already joined this team for a while. You should have some experience on this, right?
Most of the knowledge to be used are not taught by HKUSD.
So what? This is good then. Most students say, hey, the normal class is not useful. Okay, this is something useful, but don't be shy. You can say something. You like this team or not?
I like this team, but I don't like HKUSD.
Well, tell me more. Why you like this? Why you love this team?
I love this team. I personally share a lot of great memories with this team because we all join together. We like cars and then we talk about cars a lot. I find that very fun. I find it very interesting.
Okay.
One of the things I like the team is because most of us are students who know just enough to do something about participating in a competition, but don't know enough to that they are interested in learning. We get a lot of learning opportunities and a lot of encouragement when they learn something.
You're going to learn something.
For example, I'm an electronic engineer who is part of the elect team. We are not exactly competent in high-speed PCB design, but we are slowly learning how to do that. And we also have the environment to test our products. That's competent to the team. I like that environment.
Maybe. It depends. Okay. How about anybody at the back? Don't worry. We all have power engage or something. That's okay because now it's weekend. Now it's weekend. Don't worry. I will not release this thing. I'm not kidding. I mean, I want to share with us deep in our heart why we want to come or why we don't want to come. I already tell you, okay, but based on my experience, this is not for everyone. That's why I try to ask. So, Saturday afternoon, to go to swim, do some sports, sleep or something. You tell me that, come here, learning. What's wrong with you? So even though learning for most students is that I go back to homework, right? Accomplish my project. This is very important. I need to get an A. At least I want to get an 8, right? So this is for what? First of all, I tell you that you're good at these things doesn't give you an advantage that you get an 8. At least in the past, the student good at our team for develop the car, their grade is moderate. I won't say that they are poor students, but they are not those A students. And it turns out A students not doing good at this team. Do you know why?
They push too much effort in the tests and exams. They do not put effort in this team.
True. And the most difficult part is that a lot of the time that the competition, the report period, it is overlapped with the exam period. And they will say, I need to go to exam. And the rest of the team miss your design. Come on. Okay. It creates a lot of conflict for those students that care about their academics. Okay. And also some of the students care about the interest of their car, so it has a lot of conflict. Okay, so later, right now you may see this is, yeah, I can handle something. It turns out it is harsh. So most of the time, yeah, I push hard. I try to arrange my time. Okay, good schedule. Especially maybe you, yeah, I arrange my time. I put a good planning schedule or something, because this car is complicated. So a lot of things you find out that the schedule is not work, because first of all, maybe I overlook something. I think my design takes maybe 1 month, and then I try to test it in 2 months. That will be okay. It turns out my design needs to be 1.5 months. Then, and another situation, maybe I'm on schedule. Okay, you're good, but Leo not developed. Okay. Maybe something like this, because he's not aiming to that. He tried hard already, but maybe somehow he's stuck in somewhere that cannot deliver what you need for a design. Okay, so actually you need to help him, but you say, I have a lot of homework. I already scheduled myself. This is very good. I hate you. You pay my schedule, right? And now the car is not work. My homework is stuck. How can that be? Okay, so you really needs to be very love these things. Okay, and love your teammate, trying to help each other or something. It seems like it is very easy at this moment. So we work as a team. We should be working like that, but it turns out when you are very sleepy, your grade is going down, and your car is not delivered, everything's well, you find, why I come here? Okay. This happened in the first year. This happened in the first year. Okay. So, but I should say, for those of them who really accomplish all these tasks and hate and love or something, they become very good friends. The competence on the and I mean product development and engineering design exceptionally good, because they know the reality. The reality is like this: chaos. When you try to develop, I mean, really make something that people want to buy or that can win other people, you should have a lot of up and down, page on off, money. So I talk about money. Some people even make his own donation because he don't want the car to die, and we run out of money. So a lot of people, including me, I pay some on this car. Somehow we need to be okay, but we, of course, we try not to do that, but up and down somehow like this. Okay, so we still want to sit here. We still want to sit here. Okay, I hope you still can stay. Okay, hope you still can stay. And so I haven't touched this team for a while. Okay, so how is it operate right now? How is it operate right now?
So we will first design the product, and then we will do so the CAD for the car would be fully developed by the end of this year. So it's 2022, and then we'll go into the manufacturing part. So it's expected to take about 2 months, and then it goes into assembly for about 3 months, and then we ship the car to race. So this is our time schedule. And then for how our team operates, we operate in sub teams. So each team develop their own part. So if we are a suspension team, we develop the suspension, chassis, so on and so forth. And then if there are some clashes between our designs, we would regularly meet around twice or even once a week for a PIC meeting to discuss about how we should change the design. So this is how we operate during the design phase.
Okay. Okay. So any other comment on this or additional information about this? It seems like people in the back are so silent. So first of all, let me ask, you think the operation like this work? You believe it or not? Why? For example, let me ask the question first. So ultimately you will leave this team. Okay, when you leave this team, what do you expect for the return? So you invest time and your anything. So this is an investment, right? So the weekend time or your study time invest on this. What do you expect for the return?
Maybe the experience in designing a product or even car.
Okay. What else? What else?
Should we ask maybe the new members as well?
Well, on the Zoom,
Update that,
the Zoom people can also speak out if you want. No. No. No.
is anyone trying to like work in the automotive field in the future, or someone who wants to do that? What?
It's not like it's.
So I think that's okay.
Target
So
everybody.
you want to be working something on the automotive industry or something that you push through for this team. Yeah, reasonable. And any other opinion? Any other opinion?
We ask each one of them.
It doesn't matter. Okay, it doesn't matter. I think maybe for some of you, you share similar vision that's similar to Leo and Jason, right? Okay, so let me share with you that what our ambition in the beginning of the Gen 1. Okay, so we're trying to do more than what you want in the past. Okay, so the first thing, let me see. This is the presentation that we present.
Yeah, it's the first
Okay.
time we saw it.
Let me zoom it. Let me zoom this. This one, right?
Yes.
Yeah.
Okay. So this is the presentation that we present to our team. Okay, so we go to 6th floor and we tell Dean Chang, so Tim is here. So he interested on what we're trying to do for this team. Okay, so we try to let him know our goal on this team. Okay, so we list out a 5-year goal. So first of all, we're trying to go to competition. Okay, so about the competition, we're looking for building a car to go to competition. This is what you are looking for, right? Okay, no problem. And we already have some background on this. Okay, so we have a lot of price already. This is on the simulator. Okay, so at that time, we have good driver. We don't have car. Okay, and also we have a training on this. At that time, we have the experiential course about race car. Okay, so we develop full experiential course 4000 F and 4000 K that is related to some car design. Okay, so we have some basis. Okay, we have some setup, and we join the GCE. This is what we are going to design. Actually, from the beginning, we only support by the Department of Mechanical Engineering. Okay, and later on we joined the GCE, trying to get more support from other departments. Okay, so We also reach out for secondary school students. So why is that? We want to tell them we have this team. We are trying to look for good students in the secondary school, join HKUST, and become our team member. Okay. So we also reach out rather than just do the car. So this is what you say, okay, we developed this car trying to be augmented learning. So learn something real. So we really do the development. We are trying to do peer-to-peer learning. So actually most of the learning is not from me. Most of the learning is from you teaching him teaching you. Okay, so you share your experience, share data, share your analysis. This is how the team develop. Because the car is so complicated. Okay, if I can do it myself, I don't need you. I just draw everything and then ask DMSF to build a car and then take lectures to go to a competition. It's okay. Why? How come I need you? Because one man cannot do everything. This car is so complicated. Students need to learn from themselves and helping each other all together to build this car. Okay, so you learn from building this car, you learn from each other, you also learn from yourself. Okay, because it including a lot of things that you don't know, and also not teach in the HKUST curriculum. Okay, for example, how to build a accumulator. There's no such class. We have a lot of good battery research or something. If you ask the professor how to build an accumulator, they don't know. This is different story. Okay, so you need to learn by, so you may watch YouTube, you may see some paper, you may code everything, try myself, get hurt. And ultimately, oh, okay, I know how to do it. This is, how is that? So this tool is the most important. Okay, so people try to hate themselves and hate your teammate, start from here. Because this part, it turns out they cannot make it, and then start to blame on me. You didn't teach me. I don't know. I don't know how to do it also. For example, you're electronic. I'm not the electronic guy. I don't know. Frankly speaking,
You learn something on your own and you don't actually use it.
most of it is learn from your own. So I give the direction, what I need. And then based on my direction, you give me the execution, how to do it. My job is that this is not good, this is not good, this is not good. Fix it. So turn on and turn on, your things getting better and better. I hope. But a lot of time you hate me.
I just look at the things.
You will in the middle, you will hate me. Okay, but at the end, when you accomplish this, then you love me. I give you good direction. But sometimes you may leave already.
Because we are a student organization, we're not a class,
Yes.
not a course. There's no definite relationship, like study is the advisor, he must teach me something. No, we are organization here that different interested students try to learn and achieve a same goal. So in this process, we really need your contributions, and what we can do is based on our experience, what we have learned before, and we try to give you an advice only.
Yes, yes.
Based on my experience, seems this direction is better. This is our job, and your job is telling me that you are wrong. Follow me. This is what we expect from you.
Yes.
We are mutually the communication is mutual. You tell me I'm wrong, and I'm telling you you're wrong. Prove each other's, and then make the things happen. So peer-to-peer learning and self-learning is important, because let's say in this way, if I tell you to do something really, really wrong, you will challenge me, right? Why I should do that, right? This is how you learn by yourself. You are preparing to be an engineer in the field, which accept people criticism, right? And this is your job to telling me that you are wrong. Based on my experience, I deserve to call myself an engineer. Plus, I can tell you the logic is like this. This is what we expect you can do.
Yes, yes. So for example, this week that powertrain teams come to my office. Okay, they are very happy and tell me that they fixed tensioner. So my first question is that why we need a tensioner? Okay, so maybe you hate me. Come on. or you or something. Okay, this is very common. I'm the one doing the QC. Maybe in this moment you're looking for me. You think I'm the one that teach you to do everything. It turns out I don't teach you much. I just give you direction and then criticize. And then you find out that, come on, how come this teacher don't teach anything and just working on it? But this is how the nature of the engineering development. Okay, so a lot of the details that you need to watch over. Okay, a lot of things that you need to try to accomplish, learn by themselves and fix all those problems. For this, okay, this is how we tell the School of Engineering, so they understand. They think this kind of learning is good. That's why they support us. Okay. And yeah, you also do something like this. Okay, for the initial training or something. Okay. We also have a lot of outreach. We have relationship with this motor center. Okay. So this one is actually, it is not a normal maintenance center. They're helping the CLP to fix all their cars.
That's why.
So this is a big one.
Okay.
CLP tell us this is a good one. Okay. So you say, this is what's so they're big actually.
Let me add some background about that. So most of the EV you buy right now, the service centers themselves, right? You get a Tesla. Then if you want to do maintenance, you need to find Tesla. If you have a Volkswagen e-Golf, you need to find Volkswagen again. It's because the whole system is built by them. The complexities of EV and they cannot compatible with other components, right? But this is the first service center say, let us try to find a way to fix that. Try to bridge gap the motor one and the EV one, because the operation car that CLP use, some of the parts can be used the gasoline car components. They are trying to do something like this. What in their mind they try to be like, is that EV also possible to get maintenance in the service centers outside of their brand? So this is the
service centers we found, we have discussions. He is willing to help us at that time. Yeah. So this
Well,
is why we found
actually, why we pick this four, we are not just taking the picture. We really have a lot of communication and connection with them. So for example, CLP, first of all, they sponsor money for us. And that's why we tell from time to time, we try to report them. So where is your money? How we spend those money? What kind of development we done? Okay, so your 50,000 not go to the sea, not go to drink. It should go to some technical development. So actually, we did that from time to time. Okay, and CLP, actually, they don't do the car, they don't make battery, but they know these people. For example, the Volkswagen. So Volkswagen selling electric vehicle. So at that time, they tell me that, oh, they have a EV maintenance. There's somebody send the car back and the battery needs to be repaired. So this is a good opportunity to see how Volkswagen repair the battery. So because of CLP, we can go to Volkswagen and see how they open the battery. Okay, and then also Volkswagen will tell, by the time we talk to the engineer, okay, so the safety is like this, requirement is like this, so at the detail, where to buy the gloves, where to buy a qualified screwdriver for battery. These are the information from Volkswagen. You ask CLP don't know. You say, how come CLP don't know? CLP is talking about the voltage in 2,000, more than 40,000. So their screwdriver is not going to useful in EV, but they can tell me where to get the EV people and let us know. And also they bring us to mainland China. This company actually make car. So you know the Nissan High Ace, the truck, the mini truck, minivan.
Yeah.
Okay. So this company make the electric part, electric version. Okay, electric version. So why they invite us to go to this event? It is because they are helping me to ask this company to donate the battery to us. Okay, ultimately, they didn't sponsor the battery to us. Why?
There's like, it's different
That's
from
powerful.
it's different to our battery.
how different it is.
The discharge rate.
One of the formula, right? Can you think of another reasons that why their battery cannot use in our car?
Weight.
Weights, and then keep going. There's no perfect answer. Everything can be voicing out.
The passenger cars, they put the batteries in the engine bay, right?
No,
No, they just.
they're in a base page.
Some of them on the
The
front, they go
dimensions.
in the front.
We can't fit the dimensions into our car, I think.
Where is too big?
Yeah, the volume, yeah. Anything else? Can you think out of that?
Discharge, C rate, energy capacity, energy density.
Yeah, they said about that is correct, but the most important thing is about heat dissipation. We are raising car. They are cylinder shape, right? We are pulse cell. Why we use pulse cell? Because of heat dissipation. Your car doesn't work like very steady. The power consumption is steady. We are like this. This costs more hit than the operation. That's why we cannot use that.
Well, these are the information that we learned from this trip. So, but in the first hand, their boss, well, we cannot sponsor you the battery. The first impression is that you don't want to give me money, right? How come your car is using in a UV and you tell me that your car is not suitable for electric vehicle? You're lying, right? So you Chinese people, this is my first impression. And then when we have discussion with the engineer and we understand more, this is reasonable. Even though you give me, I will not use, because this will burn my car. Okay. Okay. So these are the activities that we learn from the outside. Okay. And
I can say one more thing is about the battery. At that time, we are so confident to use the cylinder shape battery, the whole design, every FE, catering, all done. At that time, we're like, okay, just get the battery and then we can make the car. After that trip, Stanley and I just so depressed. We cannot use that cell. All the catering, all the design need to change. So this is what Stanley said in the beginning. It's always debate, it's always something new, it's always changing. So maybe it's not like the class where you have, like, we have a very clear endpoint, your checkbox, done. No, we are always keep updating, keep changing. So it might be a little bit challenging for you too, but it is really good learning process because you keep getting new information, keep improving. So things happening this way.
yeah, because we spend like 3 or 4 months using a battery shape like this. We are going to buy actually almost. And somehow CLP will say, don't buy it yet. Maybe we can ask them to sponsor you. Then we are. It turns out we don't get the battery and we work the whole thing. So is it a good news for you or not? I don't know. Okay, you learn a lot, but it turns out that, oh, okay, my 4 months dumb away altogether. Okay, but the thing is like this, your development, because we are amateur. Okay, so maybe Jason say, okay, we decide using 3 months or something, then you may surprise. At the end of the year, oh, do it again. Okay, so you need to love that. Okay, so we have a lot of sharing. Okay, for example, these are the sponsors for our school. Okay, so why we care about the school? Very important. If you maybe the suspension guy already know something. Okay, so this for race car, actually we need some special school. Okay, special strength and special locking mechanism on this. Okay, so at that time, actually, we think the Seiko school is not good enough. That really, it is not the well-cast quality, I would say. For well-cast quality, it is like, but Seiko, they sponsor. So if well-cast quality is 100%, Seiko's already 90. Not too bad. So from our starting, of course, so Mr. Lai share to us how to select the school. So do you know how to select the school? There's a lot of learning from there. So most of us thinks it fit, then it is okay. But is it that simple? Okay, maybe. Okay, so this is how we are trying to. This is the group photo in the past. Okay. What the important thing is this. Okay. So at that time we are in the early 2019. Okay. And 2023, we tell the dean, okay, we are going to win in the world. Okay. So
That's university custom made their own.
So I start here. That's why I do a lot of work. Because I know for 5 years, actually this is tight, the time to come to here. Okay. So, but start from this year, it becomes Professor Taitan. Okay. He slowed down a little bit. Okay. And then that's why you get away. How can we get this? So Dean will ask me to present again. Okay. So where's our trophy? We need to deliver a trophy. 2023. This is what we make our wish in 2019. So I still trying to get these things done. Okay, you will say, okay, this 3 years is pandemic. Can we get the excuse? The answer is, so it is pandemic. Can I ask you to delay your graduation for 3 years? Okay, most students will say no. Okay, that's why you're still here. Okay. So the difficult part is like this. Okay, so you may ask. So, Stanley, you say the thing is so difficult. What kind of technical detail you have done, right? So you say it's so powerful. What? So is it? So what is your cat? What is your something? Okay, let me show you something. So open. Where's my slide? Let me see. One. It's my fault.
By the way, may I know that is that the past, you guys have joined team or you guys have
So this is, if you look at the date of the file, this is at the October of 2018. Actually, we start our group in spring of 2018. So it is around 9 months. This is not, the thing is not finalized yet, but most of it accomplished, at least in some scope. Okay, you look at number of page, 469 page. Okay, so you know how hard it is. So I just briefly go around what are the intellectual properties we have in this group already. Okay, rather than we do it in a new way. Okay, so we have chassis, aerodynamic, accumulator, drivetrain, brake, suspension, steering, impact attenuator. So these are the basics that we have designed already. So the design is just like the CAD drawing, and then based on that CAD drawing, we put it back for the verification. So the validation, what kind of, so you will ask, what is validation? Okay, validation means that when we set up our component, we should satisfy some specification. Okay, so in order to satisfy this specification, we need to do some analysis. First, to make sure that it is okay before we try to integrate, not even make it. Okay, so maybe every one of them okay. After you integrate, there's something more to fix. So you expand it, make it, spend a lot of this type. So what we are in the nature of this team, we follow PDCA. Then do this is our management philosophy. Okay, plan is our brainstorming, how to make it, how to accomplish it. Do is you draw it, you accomplish it, do some analysis, make it on the CAD or make it on paper, and then verification. Okay, you can verify by making prototypes. You can verify by doing some simulation. You can verify for whatever. So in your do stage, you always try to set up some testing points so that you can check. It's just like this is the syllabus, and then this is the lecture. This is your midterm, and this is your score. So based on this score, you go back to study. Right? And then you lecture again. This is final, and then you get your final score. If you still fail, then next year you come back. This is work for design build test of you and also design build test of the car. Okay, so this is something that we did in the things. Okay, based on this PDCA. Okay, we always follow this PDCA and we always ask you what is your checkpoint. So if it make, then finish. If it is not make, then we try to change something. Fix it, do it again. So very tedious. So we also set a CTQ, Central Technology Qualification. So it is like the thing of our car. So for example, iPhone 14, our photo is better and better. So they have something. Our thing for our car is simple and safe. Okay, this is always true for safe. I don't want you to drive the car and then you get hurt, right? And then simple doesn't mean that easy. So F equals to MA is powerful, but simple. Okay, simple and safe, this is our CTQ. Okay, maybe we can discuss about whether we should change our CTQ from this year. Okay, but think about it. So we did a lot of chassis. Okay, and it turns out, based on my experience, start from chassis, it is not correct. But at that time, we don't understand. That's why we start from chassis. Why we start from chassis at that time? Because we're thinking about we need some things in the middle so that everything can put it on. Okay, but it turns out start from a chassis is not a good idea. Okay, I can tell you why later on. Chassis should be later. Okay, chassis should serve us rather than we serve the chassis. Okay. Right, so
Yes.
so suspension people understand. Okay, so the chassis. The chassis, first of all, actually, people will think about personal rigidity. So we did FE on this. Okay, so for this kind of page chassis, the high torsional rigidity, it is not difficult. Okay, why we ask for this? It is because we want to make sure that it is not too soft, and also make sure that we know this number will be fine. Okay, so actually, JJ did this thing. So in the beginning, he get a very good torsional rigidity design. Okay, so anybody know how much the value he got?
You just showed it, I think.
Huh? You remember in the beginning? So anybody, I mean, you play around with the FSEC for a while, right? What is the value for other teams?
Other teams like for space frames at least 1,000, and for model cost I think that's 5 to 10 times of it.
How about the others? Not quite true. Quite true. Anybody know? You don't know? Come on. You got, huh?
Greater than 1,500.
Yes. Well, a good page for torsional rigidity around 2000. And JJ accomplished 22,000. 200 to 2,200. 200, 2,000. 2,200. Okay, so actually we don't need that much. First of all, you compare to monocots. So the monocots of FSAE, not the monocot of some street car or good race car. Okay, monocot of FSAE, the best team in the world. Okay, the Grimshaw ETH, their torsional rigidity around 1,600. That is already good enough.
Which team was it?
ETH, Grimshaw. If you look at YouTube, they have the 0 to 100 in 1.5 seconds.
You mean green team?
Yeah,
So.
Grimshaw. I think I don't remember it is in 2015 or something. Okay, so they are the first one use 4-wheel independent drive. Okay, so the torsional rigidity, one of it. So actually, we did reduce the torsional rigidity because we are going to reduce the weight of the cage. So we can reduce some bar so that we lost some torsional rigidity and get it lighter. Okay, so a lot of FE for this cycle. Okay. So here is the final design like this. Okay. The final design have one problem here. So this is drive wheel, this bar. Okay, we make it too fat.
Oh, okay.
And that's why we always have bad ergonomics.
That's why.
So you can be a little bit higher. That's it.
Yeah.
Okay, won't change that much for torsional rigidity, but help a lot for the tension and ergonomics. Okay, so this is my only comment at the end. Because at that time, because this bar is so low, we have to choose a small steering wheel. If the wheel is large, then it is over the bar, finish. You can't disqualify. You need to use a small wheel. Small wheel, difficult to turn. That's why every driver say the steering wheel is so heavy, because we need to use the small one so that you don't have a cut off here. Okay, so this is one of the failure after this is one of the failure that we find after we fabricate the car. Okay, so what else? So 5 versions, 5 cycles on this. So what kind of fulfillment we have? So finally, around 1,700. That is what we compromise for the torsional rigidity and the weights. Okay, so because other people, the world champion, only gets 1,600, 1,700, enough. Higher is better, dependent on what you need. Okay, so aerodynamic. Okay, Aerodynamic, actually, we did a lot of design on this in Gen 1. But it turns out you don't see much of the aerodynamic kit on the Gen 1 because later on we find out that we don't need that. Okay, so this is the first gen aerodynamic kit we designed. Okay, and it looks like this. A lot of details that the student put on. Okay, and the key is this venturi at the bottom. Okay, so you make the aero kit. There's two goals. One goal is get the downforce. Another goal is try to put sticker so that you get more sponsor. This is very important, right? Okay, and your car looks cool, more people want to sponsor you. So aerodynamic kit is important in the sense of sponsor. Okay, more than the downforce, and my point of view, at least at this moment. Okay, so a lot of things we did CFD. Okay, we set up a lot of details how the CFD done. Okay, how to do the CFD. We assuming that the gap here around 0 to 5 cm. Okay, so we change this gap to see not from 0, from 30, not from 30, from 15 to 50 to see how the downforce change. Okay, because simulation cannot simulate the sponsor, only can simulate the downforce. Okay. Okay, so looks cool. Okay, looks cool, and we did verify, ask a lot of questions. I think his simulation is believable. Okay, so these are the downforce jet force results. Okay, then based on this second gen, we again change his diffuser direction, change his wing shape. Okay, change his mesh, the force distribution so that it can evaluate. Okay. So the velocity field, because this guy is just aero student, so he know a lot about these things. Okay. So try to set out the coefficient. Final design. Adding how to mount it. The aero kit, the difficult part is we don't know how to mount it. So ultimately, the final design, we have this much downforce. So 500 Newton, 50 kg, not bad. So for the aero design teammate, if you are not start from here, you don't need to see me. Okay. you overcome this one first. Okay, this is the design we have. I still have the cat. If you are not overcome this one, you just copy. Okay. Okay, we have a good downforce like this. Okay.
Or maybe we just decode those boundaries.
So you may ask, this is what the gap is. It is around 30 mm gap. That's why we always care about the gap between the ground and the base plate, because it makes huge difference. So if it go up to 50 mm, this one almost nothing. It will drop fast. It will drop fast. Okay, so we fulfill anything that we try to get on. Okay. So battery. So this is why I say so the funny part is that we try to set out the power situation based on the vehicle running on the endurance test and endurance race. And you say we don't have a car, how can we get that? We try to make friends with other team and try to use their data. Okay, so one of the Chinese team, they are nice to us and then share their power data to us doing the endurance. So this is how we simulate the heat generation. Okay, and also at that time we assume we are using the Tesla battery. Okay, not the pulse battery. Okay, because we don't understand. Okay, so a lot of things.
This heat simulation is done on Abacus as well.
Yes, heat transfer. Heat transfer. So 60 something degree. That's why at that moment we believe we don't need the heat dissipation on the battery. But it turns out the charge discharge. So the heat generation is from the charge discharge, right? So why we have heat? Because the internal resistance of the battery. So if your battery it is a resistor, part of the resistor, it will generate some heat. And it turns out this is non-linear. We assume this is linear. And the bad thing is that when your battery is discharged a lot, for example, your iPhone discharged like more than 50%, the internal resistance getting higher. So that means for your endurance test, you start with your battery, that is cool. Okay, and heat generation actually is small. But later on, when your endurance getting near the end, so your battery almost out, so you only leave around 30% or 40% of your battery. Actually, the heat generation is faster. So it is very tricky. So at the beginning, you see, okay, oh, how much heat? So the heat generation is like this, and then okay, it is non-linear. How we know that? When we go to buy the battery in Melissa, the supplier that we bought, they give us the charge discharge data, and then we know. Okay, and we are glad that we have those data. Otherwise, our battery even worse. Okay, so this is something tricky and surprise from the battery. Okay, so we still try to pack it like this. It turns out we waste our time. but it doesn't matter. How that box put in the cage of our cars, the chassis, the supporting, you need to fulfill the regulation. Okay, the regulation also asks you this battery mounting need to sustain, I don't remember, 8G of the force. It is quite tedious. I don't know whether you have that design analysis yet or not. That's why we put a lot of anchor at that time. Okay, so the battery, not only making the battery, you're also trying to make the arrangement so that it can have support the heat dissipation, and also the mounting need to sustain for the regulation requirement. So the requirement is just like, even though I get car heat, like 8G of force, the accumulator will not be kicking out like this. Okay, so this is one of the requirements of the accumulator for structural, and also for the operation and for the electronic design that linked to it. Okay, so it come to fourth cycle, right? Okay, a lot of things. So we still have a lot of follow-up. But anyway, okay, brake system. Brake system, we do the brake system. What is the difficulty of the brake system?
The design the mounting for the brake clamp such that it doesn't fall.
It is easy. It turns out it is easy, based on our experience. Okay, the difficult part is that also the heat. Because the brake is operated like this. Okay, you have a caliper, and then when you brake, you just cam it. Okay, this friction will generate heat. And because you are driving a race car, you try to be accelerate. Something like this. So you have very strong friction on this. Okay, first of all, your brake pad. Okay, the surface material holding the steel disc, whether it will melt. Okay, if it is not, the material itself, it is not, cannot sustain the upper temperature of this material, then your brake will be unfunctional during the race. Okay, so one thing that is just the material selection. Another tricks for this design, it is that how you select your brake fluid. Okay, because how the brake work, because you step on the pedal, and the pedal squeeze the brake oil so that the caliper will clip on. Okay, so your brake fluid will in contact with your brake pad. Your brake pad is in several hundred degrees C of temperature. It will heat up the oil. So if the oil boiling, then you are done. Right? Then you're done. For Formula One, the brake pad temperature can up to almost 1,000. Okay, for our study, our brake pad based on FE can be up to 370 something degrees C. we still can find good brake fluid based on this, because some brake fluid it is for like 400, 500 you can buy, but if you go to the Shell station, get a normal brake fluid for this car, bye-bye. Okay, you hurt your driver because he lost brake. Okay, so this is we are using the dynamic simulation on the analysis. So we set up all these things. Okay, so how these things run? We just simulate the car running for a period of time. Okay, and simulate the brake camping, releasing, camping, releasing. Okay, so simulate for 1 cycle, 2 cycle of it, and see how the temperature of the brake pad rising, and also this rising. So in this test, we are combining the temperature analysis and also the structural analysis. Okay, when you cam it, you may also deform the structure, whether the caliper can hold or something, that all in one for the simulation. Okay, this simulation takes 2 weeks to run for 2 minutes. For the car running for 2 minutes, this simulation takes 2 weeks to simulate. Okay. So you may say, okay, I just do simulation, can be whatever, just try it first. It also takes time. So even though you're not working prototype, you're doing simulation. Yeah, I can do a lot of simulation, but if your problem is like this, also takes you a lot of time. So even though you click start, then you can go away, leave it for some day, but you need to wait for it. Okay, so this also takes a lot of time. If it turns out, actually I did. It turns out when I see the results, I found that my setup, I made some error on my setup. So my 2 weeks data go away and start another 2 weeks again. So it is a lot of pain like this. So you see, yeah. So you see a temperature, the rising, this is stepping on a tip pad.
What is the secondary axis on the right?
Time. So this is in second. This is the temperature.
No, the right one, the orange is 110, 200, 300. The orange one.
Same thing.
Oh, okay.
Same thing. Same thing. Okay, and also just like what Jason say, okay, how can I get the mounting? Okay, it turns out in the beginning we try to do it like this. Okay, not good. Then we fix it like this. That's okay. So not too difficult. The difficult part, it turns out to be the brake pedal. Because when you push the brakes, you push hard. Okay, we made several cycles to fix it. It turns out, based on our study, you may load it up to more than 300 newtons on the brake pedal. So you only have a bar that anchoring here, and your big pad to be here. So a lot of bending on this, and bending, it is easy to get failure. You mechanical students should know. Okay, bending no, easy to get failure, but you cannot change much on the big pedal. Okay, and also why you cannot buy some big pedal from the simulator, because for game you don't hit the big pedal that hard, but for real car you are in some dangerous situation, you are afraid of something, then and it turns out that is really dangerous. Okay, so the big pedal actually it is the weakest link for brake design. Surprisingly. Okay, you think that this campaign, that there's a lot of things that is difficult to accomplish. It is not. This one is okay. So you also have a lot of drivetrain. Okay. So drivetrain actually is interesting. Why is that? Not because of the drivetrain. It is because the student doing the drivetrain. Okay. It's not a good student. That's what he said. They will say, what the hell is that? Okay. So what is this drawing? This drawing is a free body diagram.
You can call it that. You can call it that.
Anyway.
We always starting like this. Okay, although his drawing is not good, but it is a good habit. Then we start from a paper and try to set out some free body diagram that with the load and the anchor. So later on, when I teach you the finite element methods, you understand why we need the free body diagram in the beginning. Okay, so he's a student like this. And his FE, the measuring a lot of things ugly. Okay, okay, not good. Okay, but the foundation is correct because he has the free body diagram. So this is the anchoring, the setup where the loading is, the foundation is correct. Just the accuracy or the details is poor. Okay, so this is what he began. Okay. So of course, we tell him this is ugly, this is not good, and also you need to reduce some weight. That's why we try to reduce some weight here. So the details doesn't matter. I just okay. He found the another thing. So the anchor, this thing, okay, only in the corner. We don't know. Okay, because in the cage. So actually, all the force go to the cage, and the cage boundary condition, how to set it, it is the art of this result. Okay. So you will see his analysis and drawing getting better and better. So compared to the beginning, this one looks a bit nicer, and you see his setup more and more details. Very much details. In the beginning, just some free body diagram and then give me the results. What the hell is that? Can I believe it? Okay, so this is the third trial. He improved a lot. Okay, give us a lot of details where the boundary conditions should be and tell why is it. Okay. So where are the problems? So now we start to identify those problems. Okay, the contact, the deformation itself. Okay, so this is a rough mesh. So he have some doubt whether the stress is okay or not. So he refined his mesh, and it turns out here we break. Okay, so revise in the final stage. Still a lot of things to fix, but now we are almost here. Okay, we just fix this bar. Okay, with a stronger, not a stronger bar, with a higher thickness bar, so that we accomplish this stress. Okay, and this is what he has for this 10 months. Okay, so you see his results, you see how he improved and learned. Okay, I hope you also can accomplish like this. And of course, this is something not finished. Later on, after this result, we find out one more critical problem. It is the train. The train load is very important. And also later on, we also work with him to simulate the train load on these things. So then we accomplish this. So a lot of things. For example, the suspension. You may be interested. So for the suspension, actually, we didn't start from the kinematics, because at that time we limited from the chassis and we don't understand the kinematics. So we just copy somebody's and try to revise for things. So we start from component to component. Okay, for example, we have the wheel hub, do the FE. Okay, so wheel hub, is it okay? So cross mesh, make sure everything can run, and then we do some fine mesh to confirm the stress. Okay, so why is it like this? This is the overall, so that we can, in the first tryout, see whether the model can be similar.
It's more like saving time.
Yes, and then we know where are the high stress position. Okay, and at the high stress position, we try to refine the mesh to see the stress intensity. Okay, so this is the approach we are trying to have. But you may ask, how can I know the boundary condition? For component level, at these things, we cannot. We can just assume. Okay, so you tell me that I did all this, and then I finished the analysis, then you're bullshit, because your boundary condition, you don't know. You only have your assumed boundary condition. That is not real. Just you entertain yourself. Okay. Okay, so same thing, we do it on upright, same kind of cycle. A-arm, same kind of cycle. So every component, we did the things separately. Or so we know every component we can do the FE. Now we integrate all the components into one FE. Then your boundary condition become more realistic, right? So these are the components we're trying to set it together. Okay, so all kind of material properties, what kind of elements we set in the model. So a lot of details, because you need to take the check on whether this component, the element, it is compatible. Okay, so if it is not compatible, then your design actually it is some kind of hidden error inside. Okay.
What is this element?
What?
What is this element?
On the right side.
This is the element I have.
What does it mean? C3D data.
Oh, you can check it from the menu.
Okay.
Yes.
So this is Abacus, right?
Yes, but FE people usually know.
I'm not yet.
I know. When you're familiar, this is something that's really familiar with that. This is the FE model. Okay. So you say, okay, the individual work, the integration should also work. Okay. So of course, you need to make some assumption on this because based on the integration, some of things that you cannot integrate. Okay. These are the results. So what kind of result we are looking for? The displacement. Okay, how much it can move? Okay, because we care about whether our car will touching the ground. So displacement, the stress distribution. Okay, it turns out a lot of high stress. A lot of high stress. Some of the high stress, it is from the aircraft. Okay, why is that? We have some interference. Okay, so push rod, okay. And here, the fisheye joint, the joining corner. Why is that? You have some you are picking. Okay. So this one also fisheye joint. So fisheye joint create a lot of problems and needs to be very careful. Needs to be very careful. So always there, the connection. Okay.
So is it more like the rod end actually is bending?
So it's actually like this. The fisheye joint is like this, and then this. You are
Yes.
They are going to break.
Yes.
The result is going to break.
Yes. Yes. So also in the upway, will be strong. And you see some high stress because the small fisheye joint taking these things. Then you have high stress. If you're just like this is a fisheye joint, your upway here,
Yeah,
and then you're just kicking it, touching, and then
Alright, so
okay. So we're glad that we do the full simulation. You have it. Okay. So we change everything and do it again. So actually this one almost running for 4 or 5 parts to fix the geometry and also fix some load. And ultimately, we also add some spacer on this, on the things. Okay. And we also, what important is that we also output the reaction force of the loading point so that we can check whether the bar will buckle. And also whether the force will be too much for your chassis. Okay, so steering at that time.
What is that geometry, the 2D geometry? Oh, the A command, is it?
Yes,
But it's 2D.
it is 2D because we start from 2D.
Okay.
Okay. From the gas. Okay. So we don't get it from 2D because we fixed it the front and the back. At that time, we don't know. Okay. So later on, we fixed it, this thing at the end of the day. Okay. Very difficult. It turns out this is the most difficult part. So my opinion is that not only the outcome. If you really understand is that the kingpin inclination, caster, and your camber, these three things optimization with the outcome. Okay, so only outcome okay is not okay yet. That's why you need atoms. Otherwise,
It's just kinematic steering. It's like, instead of dynamically driving the car.
But Adam's car, you can do kinematic
Yeah.
analysis.
yes.
Also,
So also the IA.
Geometric steering on kinematic steering.
yeah.
So also the IA,
But not like
this kind of IA. So how to get this?
this way.
So the IA itself, I model like this with some material behavior like this. Because this material, you are going to crush it. So you are not going to have single Young's modulus. Here is your Young's modulus, and when it breaks, it will like this, and then when you compress to some kind of level, you rise again. So it's a complex governing equation for the IA. Okay, so we do dynamic simulation. The process is like this. Okay, what we need to fulfill, it is KE. So we need to provide the heating in the simulation. We need to have a velocity that is enough to create an kinetic energy of 7,350. Because by regulation, we need to dissipate that much energy. If you are not going to provide enough energy, then you cannot dissipate that much. Okay, and we need to start from 7 meters per second. The velocity before you hit it. Okay. So my first pass cannot. So this is my goal. When I hit it, my energy to here, no. So velocity after impact, deceleration. So seven things, change the configuration. Okay, you whether this is not movable. Okay, the step like this again. Try to modify the material because Suspicious whether I use true string or engineering string. So I try both. Simulation, okay. The behavior change a little bit. Okay, see whether I can. This is what you can get from the results of the FEM. Okay, so it hit and then bounce back. Hit and bounce back. Okay. So again, better a little bit. Still not make it. Make different nodes, more material. A lot of problem that I'm going to review because I know repeat trying it is not good. Try to understand whether my simulation have problem and also what kind of sensitivity we can have for the geometry. Okay, so added more string on this, and this is the third time. Like this. Okay. So ultimately, I review the engineering balance. Okay, so actually, finite element analysis, the iteration is based on the string energy. Okay, what is it related to the total energy? Okay, so I try to lay out all the energy, which is related or not related. Try to see which one is important, the internal energy. Okay, which is the strong effect and weak effect related to all the components. So using this form, based on the literature I found from this material. Okay, so this time I add the alignment on the material and also with some friction. Say what the hell is that? So when your IA hit this, you have some friction. So you see no friction, with friction, it has some difference. That little bit. Yes. So even though no friction, it barely passed. With the friction, you pass more. If you are not aligning your material, you're not going to pass. And the important thing is that oops. Whether I can take it. So, based on this figure, I don't know whether you realize the back page become. So the form of the back page, that means it is some kind of string energy. So I saw your chassis in the front have a crossbar. If you pull the crossbar, this thing cannot be formed, you fail. This is why. So you squeeze there a little bit.
Like there's the rule if you get the front ball head too large in the bar, if you get it smaller than the required, you don't need it. So
I know,
we
but
try to-
if you failure to this, you also not pass. Okay, this is no question asked. You say I don't put a par, I fail, but you don't get a par. You get a bar and you don't get this, you fail also. Okay. Headache, right? You still want to stay here? Okay. So these are all the things that we did in first 10 months. In first 10 months, actually, the whole presentation we did more cycle on this. Okay, use it around. So from the beginning of 2018, the analysis up to almost May of 2019. Okay, so at that time, we almost all validate. For those we cannot validate, we cannot validate. Anyway, okay, so this is what we have. I believe you may start from here, rather than you try to be on a blank paper, because you already have a lot of things. So you improve from here, rather than you spend 1.5 years to doing and it turns out it is not up to here, then you we waste of our time. Okay, so of course I can share more information and the model to you about this, but this is what we already have. So these are what the properties, I mean the reserve that we have in our team, the knowledge, the reserve, the understanding, the data that we have in our team. So we can base on this. Okay, so the another knowledge is what I think you need to start. It is like some basic learning. Okay, for example, learn some design. Okay, so I will try to go over.
He should turn off the mic or.
Hello. Okay. So before I end today, we also need to make some sense. I think for us, the design people, we need to make some sense. For example, let me go back to basic. So when you design your car, how can you start?
Orientation, know the aspect.
Know how to put where the wheels are and where the wheel lays.
But now you only have a bang picture.
Then you
Decide
can
which
know
direction
where
it
the
is.
weight lays.
Design where.
So what I do is just sketch something, right? Sketch something and for
Oh, this is the
If
front.
you would like to. Do it like this, right? So this is a portrait. Maybe we try to say be simple. Pin joint. Okay, so this is mounting to the upright anyway. You understand what I mean? Right? Right. Start from this. Okay, this touching the ground. Right. Right. So you're year 4, right? For volunteer. How many degree of freedom?
I've got all those stuff.
You want muscle? Who learn physio? You guys did into midterm, right?
You guys remember, you answer.
Come on.
Sounds like and
Suspension.
I really think about that first. I think about the weight first. Like,
You know why I asked this? Actually, it also start from physio from chapter 1. Maybe you think because it is in the book in chapter 1, that's why we learn this in the beginning. But we have a reason.
how do you count degrees of freedom?
We have a
如
reason.
果有條識噶嘛30嘛，如果係 2D 嘅，
And then we give you n minus j minus 1.
係啊，
係啊，
呢個嘛，
Right? Well, let me tell. Maybe this is a homework. Okay. So especially those of you who are mechanical engineering students, this should know. This should know. How many degree of freedom? This is my first question. We start from this, and then actually I want to talk more about this, but maybe you do the homework first. We come back next time. Based on this, how we start on ourselves. Okay. Copy this diagram. Copy this diagram. And then I think we come back 2 weeks. Next week in the weekend, I have problem. I have my schedule for another student society. So maybe in 2 weeks, we come back and start here. Okay, I think you want to learn why I asked for DOS. I think you saw a lot of these things in Google search, especially for car design, road center, suspension design. Every people give this kind of diagram, right? I test your understanding and why we care about this and how to make sense about this. Okay. Any question? Any questions? Interesting? Or you don't, that's why in the beginning, if you don't find these things interesting, don't come. It is tedious. So you are going to make that 500 PPT also. Okay. And still you see those data seems very details, a lot of sense of this, but still the car is not that good. See? Okay. So you copy already? So let's go. See you. See you. 拜拜。
我自己點睇咧？即係如果個方案就話呢一度係呢度。